All right, this video is on the wave nature of light. And the first thing we're going to look at is Huygens principle. And what Huygens principle is an idea that at every single point on a wave, that point is generating a new wave front. So in this diagram over here, you have, imagine a pond, all right? And this here is the initial source of a wave. What would that be? Well, you threw a rock into the pond and you disturbed the water, and the wave front comes out in a circle all around, and it gets bigger and bigger and bigger, right? We know what that looks like. Well, Huygens principle says that if we were to take any point on this wave front, we can look at it as if it's creating a new wave front. And usually what happens is you get some interference with these waves here and you just see the circular wave front. But if you could get rid of that, you would see from any single point a new wave front coming through. All right, so let's look at what that would look like. And the easiest one to see this on is the far right, C over here. We'll go back to A and B in a minute, but let's look at C, where we have a wave front coming this direction, and we get rid of all the other waves except for this one point, okay, this one point, and this one point gets to go through this little slit, this little opening here, and this one point comes through, and you see it creates an entirely new wave front. All right, that's Huygens principle. If you get a longer slit, all it's showing here is if you get a longer slit, what happens is you get more of this wave coming through. What's interesting here is you can see that you get the bending on the corners, and this is diffraction. This is classic diffraction, bending of waves. And in this case, A, you only block the top part and you get this whole wave comes through, and you get again this classic diffraction. And the way to think of it is from this one wave point that comes through, we create a whole new front. All right, this is part of the new front of that wave. Okay. So here we go as we think of Huygens principle and the law of refraction. When something enters a new medium, remember it slows down, and that bends the entire wave front. So the way I tend to look at this picture is I imagine my kids, truck or little toy they're playing with, and this part is my lawn. Medium 2 is my lawn, and this is asphalt. And as the truck comes, the front wheels hit here first, and it slows down, and it will turn, into the lawn. Just because the way I vision this, it would be the right front tire hits first. Well, the same thing happens with a wave front. Here's your wave front. This side hits first, and it slows down. We know that light slows in a more dense medium. So as you look at the principle, Huygens principle, and you apply it to the law of refraction, it explains the law of refraction, right? If you think of each of these little wavelets, these little waves that are propagated from each new point in a wavefront, the ones that hit the new medium first, as they come in at an angle, the ones that hit first are going to slow down first, and that will cause the entire wave front to bend. Okay. So we can do the same math with that, right? You have the frequency of the light does not change, but the wavelength will change as it enters a new medium. So you can actually cause like color shift. This is how we can take a prism and we can bend out all the colors of the rainbow using it. All right. You can also use this principle to explain mirages, and a mirage is due to heated air. It works really well in a desert, but it also works really well when you live in a really hot flat area and you're looking at black asphalt. What'll happen right above the asphalt is you have heated air, which has a different index of refraction than cooled air. And remember, your eye will not take into account the fact that light has bent. So whatever enters your eye up here you are, whatever light enters, you assume has come from a straight line. Well, this light is actually bending. It's actually bending due to the rising air. The index of refraction is causing it to bend. That's the principle, Huygens principle. It's hitting slower, a higher index of refraction. The wavefront bends. It hits your eye. Your eye simply interprets it as having traveled in a straight line, and so it thinks it's come from down here, and you see a mirage. A lot of times what it'll look like, sometimes you'll see like a car or something like that, but a lot of times it'll look like there's water there. And that's why people in the desert, they'll always think they see water. This rising heat here tends to cause the waves that hit your eye, the light, to look wavy, like it's water. And that's just because the index of refraction keeps changing ever so slightly, so it looks like it's bouncing off of water. All right, interference. Well, we know when waves interfere, you can have constructive interference and you can have destructive interference, just like in sound, okay? So we're going to look at waves that interfere and how they're going to interfere constructively and destructively. So here we have some waves and they're hitting two slits. This is a very, very, very famous experiment. You take something and you have two slits, and these are fairly close together. You can actually do this on an index card using razor blades if you're careful. And the waves hit here and they go through these two slits. And the question is, what do you think comes out the other side? Do you think when the waves come here, knowing Huygens principle, hint, hint, do you think you're going to get two slits over here on the other side? And of course the answer is no. Light is a wave, and when it comes out, it spreads. Those little wavelets spread. And as each of these spread, they interfere with each other. So you actually have a wave front that comes through slit 1, and you have a wave front that comes through slit 2, and you don't get anything at all that looks like that, or if you do, you did it wrong. What you should actually see are bands of constructive interference and then dark areas of destructive interference. Okay. So this is what that looks like. Made a little larger so you can kind of envision it. You should get an interference pattern. You have, if done properly, slit 1 and slit 2. And, if light were like a bullet, right, it would just go through and hit your screen here, and it would go through here and hit your screen here, and you'd have two bands. That's not what happens. These waves come and they interfere with each other. And where they interfere constructively, you get a bright band. And where they interfere destructively, you get a dark band. All right, so this is how it looks. We have some waves coming in slit 1 and in slit 2. And we're going to look at how they interfere again. This is a different visual for the same thing we've looked at in the last 2 slides. But you have the light coming in. The D here is the distance between your slits, okay? Light's coming in, and hopefully it's coming in phase. And when it comes in, if it ends up being together in phase over here, you should see a bright spot here, all right? And we know light bends. And remember, these are also represented as wave patterns, wavelengths that look like this, little wavelets, okay? Now we're doing the up-down transverse thing so you can see them being in phase or out of phase, all right? So now if we bend this wave, and we bend it an extra distance of 1 exact wavelength, well, it ends up in phase again, right? If you're 1 wavelength shift by the time you hit your screen, beautiful. You're back in phase. You're a bright spot. It's only if you're an extra half a wavelength off, then your crest is going to hit your trough, right? And so the crest of this one hits the trough of this one, and what you see there is a dark spot. Those two will cancel each other out. They interfere and cancel each other out. All right? And so you can do, your little bit of geometry to figure out where you're going to have a bright spot and where you're going to have a dark spot. Oh yeah, here's your fun little bit of geometry to figure out where you're going to have your bright spot and where you're going to have your dark spot. Your dark spot is going to be a half of a wavelength off. All right, so for constructive interference, and because you have sine, right, it's not, it's like a continuous wave, right? So you have areas that are very, very bright, and then they fall off pretty rapidly to areas that are very, very dark. But it is a continuous thing. It's not an instantaneous thing. So you're going to get a little bit of shadowing here on either side of your bright spots. But pretty quickly, you're going to go from bright to dark and back to bright. So this is another way of thinking about it. These are, the crests here represent your bright spots, your constructive areas of interference. And the destructive interference represents these spots. So again, same pattern repeated. You can tell we like the double slit experiment. There's like 5 slides on this thing. All right, well, if 2 slits is fun, then 1 slit can equally be as fun. So now we have light going through 1 slit, and you think to yourself, well, it can't possibly interfere with itself. Sure it can. Not nearly as well as the 2 slit experiment, but you actually can get interference from 1 slit. And you'll have a very bright, right in the center, very bright, very intense, excuse me, very intense pattern on the screen here where it comes through. But then you'll end up with these little kind of blips where you get, oh, there's a little bit there and it gets dark, and oh, there's a little bit there of light and it gets dark. That is it interfering with itself. Okay? And so for a single slit diffraction pattern, there is your lovely equation. All right, now this is why bubbles look pretty. This is what you really need to know in life, why bubbles look so awesome when they're clearly just made of a clear substance. Soap in the water doesn't have all those pretty rainbows in it, and yet we see pretty rainbows all day long when we look in bubbles. This is why. You have to be talking about something so thin that it's only a couple wavelengths thick, okay? So not a piece of glass, that's too thick. But something very, very thin, you're actually going to get interference that is going to cancel out some of the colors of light, certain wavelengths. So maybe it doesn't cancel out red, it cancels blue, and then you see red. Yay. Very, very fun, very, very pretty. So let's look at what this looks like. This is going to be oil on water. This is like an oil slick, and when you look at the road and you, oh, look at that, it looks pretty. Same idea though, this works for a bubble too. All right. You have a couple things going on. You have light. No, it's not shooting out of your eyeball. It's just coming from somewhere up here, okay? And it's going to go to your eyeball, so follow the arrows here. We're going to hit a surface. Some of that light is going to bounce off the top of the surface. If it's the bubble, it's going to bounce off the top of the bubble, okay? And towards your eyeball. Some of it is actually going to go into the oil. And remember, as it enters the oil, it's going to bend. This is refraction. It's going to bend. It's going to hit the bottom of the surface. You're going to get a little bit of, remember that internal, when we talked about optics, and you can actually reach a point where it'll bounce internally inside of an object. You can get that. It'll bounce back up towards your eye, and now you have very close to each other 2 wavelengths coming towards your eye. Well, guess what? These 2 waves here interfere, and so if they interfere in a way that red ends up hitting your eye at a place where it has constructively interfered, you will see red. And if the blue has constructively interfered, you will see blue. But if the red destructively interferes with itself, you won't see the red because they're close enough together. And, obviously this is not drawn to scale. This is all, wavelength thick. So we've made it bigger so you can kind of understand how it bounces here, bounces off here. This is a wave coming up towards your eye. This is a wave coming up towards your eye. And they are going to interfere with each other, and then you're going to see the pretty colors, because really this is white light. It contains all the colors of the rainbow, but some of them destructively interfere and you'll see green or something pretty. Or maybe you won't. Maybe you'll see, white where it happens to hit and reflect all of it up towards your eye. This is the exact same thing, which is why you don't have to write it down, but done with a thin piece of glass sitting on a glass surface. It's called Newton's rings. So if you've ever put glass on glass and you see that rainbow, it's the same idea. You have a little bit bouncing off the top, a little bit bouncing off the bottom, and they interfere and you see a rainbow. Okay, you can do the same thing here, and again, you don't have to draw it because we can just keep doing this all day. But anytime you take a white light, have it hit off of two very close surfaces so that they're just ever so slightly shifted, you will create patterns of interference. Okay, here you go. How to solve for interference. Interference occurs when there's two or more waves arrive simultaneously at the same point at the same time. These are constructive or destructive. Constructive interference occurs when the waves are in phase. This is just like sound. Destructive interference occurs when the waves are out of phase. And then number 4 is just to remind you there is an extra half a wavelength shift occurs when light reflects from a medium with a higher refractive index. You remember when I was doing that slinky on the floor, how if it hits something on the echo, it'll change direction, right? And in the book it says if it's a higher index, it's going to flip the wave over, and if it's a lower index, you're gonna have it bounce back on the same side. Well, this also applies to when light is entering a medium with a higher refractive index, it shifts at a half a wavelength. So you have to take that into account when you're doing your calculations.